Welcome linear algebra fans, a video today on the matrix inverse and its relationship to non-singular matrices. So in this section, we'll go through a few theorems that we promised to prove last time that we'll go ahead and prove this time. For instance, we will see that that a matrix B has the property that AB is equal to the identity if and only if B times A is equal to the identity. And then we'll eventually get to the main result of this section, which relates invertibility to the property of being non-singular, right? And then we'll close with a new property, this property of a unitary matrix. So we'll start with sort of a little bit of a review of non-singular. The definition of non-singular, matrix A is non-singular if the homogeneous linear system has only the trivial solution. Now, of course, this has a number of equivalencies, right? Remember, equivalencies are statements that truth of any one of these statements implies truth of the rest of them. So being non-singular is equivalent to row reducing to the identity, is equivalent to having a trivial null space, is equivalent to having a unique solution for a linear system having a unique solution for all B, is equivalent to having linearly independent columns. And a key idea for today is that solving the linear system with coefficient matrix A and vector of constants B is equivalent to solving this vector equation AX equals B. Okay, so we'll start off with some preliminaries, again, proving a few theorems, and you'll get a chance to try your hand at parts of these theorems as well on the worksheet, so watch out for that. Here's the first theorem. Suppose that A and B are size n. Their product, AB, is a non-singular matrix if and only if A and B themselves are non-singular. Okay, so this is a statement of the flavor P if and only if Q. We're going to prove the P implies Q part together. And the way we'll do that is sort of interesting. So we'll actually prove that by using the contrapositive and proving instead the negation of the P implies Q statement, which is not P implies not Q. Okay, so again here the twist is that we're going to prove the negation of the statement truth of P implies truth of Q by proving that not Q implies not P. So we'll assume that A or B is singular, and then we want to show that AB is singular. So here's part one. For part one, we'll go ahead and assume that B is singular. Okay, of course, if B is singular, then by definition, the homogeneous linear system, where B is a coefficient matrix, has a non-trivial solution. Let's call that solution Z. That is, there's some Z, that Z is not the zero vector, such that B times Z is equal to 0. Right? That's what it means to be a solution of the homogeneous linear system. Okay, of course, we can go ahead and have a look then at the image of this vector under matrix multiplication by A times B. We see that AB times Z is A times BZ, which is A times the zero vector, which is of course the zero vector, so that Z is a non-trivial solution of the homogeneous linear system where AB is a coefficient matrix. Okay, so if B is singular, then AB is also singular. For the second part, we'll assume that A is singular while assuming that B is not singular. Okay, of course, we can assume that B is non-singular because if B is singular, we're covered by case 1. So if A is singular, then the homogeneous linear system with A as a coefficient matrix has a non-trivial solution. Let's just call that solution Y. Okay, of course, since B is non-singular, a linear system with vector of constants B and with vector of constants Y and coefficient matrix B also has a unique solution. Okay, so again, since B is non-singular, the linear system with coefficient matrix B and vector of constants y has a unique solution. Let's call that solution Z. And it must be that B times Z is y, right? Again, relating the linear system to the corresponding vector equation. It's important to note that Z is not 0, right? We know that y is not 0, therefore it must be that B is not 0. Okay, so we can go ahead and have a look now at what happens when we multiply that vector Z by A times B. We see that A times BZ is A times BZ, which is A times Y. And of course, A times Y is 0. So Z is a non-trivial solution of the homogeneous linear system with coefficient matrix AB. So we see that in this case also AB is singular. Okay, so if A or B is singular, then AB is singular, and that is, again, the proof of the statement that if AB is non-singular, both A and B are non-singular. Now, of course, this is an if and only if statement, so we also need to prove the statement that Q implies P. And I'll go ahead and leave that for you. In the statement Q implies P, we assume that A and B are both non-singular, and prove that the product AB is non-singular. Okay, so that's an exercise for the worksheet. This theorem allows us to prove a theorem that we stated last section, namely that if A times B is the identity matrix, then B times A is also the identity matrix. Okay, this is the theorem called one side inverse is sufficient. In other words, we only need to show that multiplication by a matrix on one side is enough to prove that a matrix is the inverse of another matrix. Okay, so we'll do this by assuming, again, that A times B is the identity matrix. So if A times B is the identity matrix, then it turns out we know that A and B are both non-singular. All right, and we know that from the last theorem because the identity matrix is non-singular. Now, if B is non-singular, we know that we can take B, augment by the identity matrix, reduce that to row echelon form, and the left half of that augmented matrix will be the identity, and the right half of that will be a matrix C that we were calling last section the right inverse of B. Okay, so it's this right inverse of B that's going to allow us to prove that B times A is equal to the identity. So we'll start with B times A, and we'll do a bunch of legal operations and show that we get back the identity matrix. So here's what that looks like. So starting with our assumption that A times B is the identity, we can left multiply by the matrix B and get B times A times B is B times I. Now, of course, on the right-hand side, B times I is equal to B because any matrix times the identity is just that matrix. And on the left-hand side, we can reassociate our matrix multiplication to write that as B times A all times B instead. We can then multiply both sides of this equation on the right by the matrix C. And once we have the matrix C there, we know that B times C is the identity because C is a right inverse of B. Now, of course, any matrix times the identity is just that matrix, so we see finally that B times A is equal to the identity. Okay, again, this is something we stated last section that we've now been able to prove based on this proof that the product of non-singular matrices is also a non-singular matrix. Okay, so the main proof of this section is the statement that A is non-singular if and only if A is invertible. So I'll go ahead and prove part of this, assuming that A is invertible and proving it's non-singular, and then I'll leave the second part to you. Okay, if A is invertible, then there is a matrix, call that matrix A minus 1, such that A times A inverse is equal to the identity. Now, of course, the identity is non-singular, therefore A and A inverse are both non-singular by our theorem. Okay, so again here we've proved half of our if and only if statement, and I'll leave the other half for you to work on the worksheet. So we'll add this to our list of non-singular matrix equivalencies. This is the newest one, A non-singular if and only if A is invertible, right? So often those two are used interchangeably. Of course, they have different definitions, right? A non-singular means the homogeneous linear system has only the zero solution. A invertible means that there's an inverse matrix, A inverse, such that A times A inverse is equal to the identity. As it turns out, they're equivalent statements, so truth of one implies the truth of the other. So a great use of this non-singular matrix equivalency is in solving the linear system LSAB. Okay, so the key to this theorem is that solving the linear system LSA comma B is equivalent to solving the matrix equation AX equals B. So since solving the linear system A comma B is equivalent to solving AX equals B, the vector equation, we can start with that vector equation, multiply on the left by the inverse matrix. Of course, A is non-singular if and only if A is invertible. Reassociate matrix multiplication. Of course, A inverse times A is the identity matrix, and we end up with X equals A inverse B. Okay. All right, so we'll go ahead and finish up with a short discussion of unitary matrices. This is a new class of matrices. If U is square and the adjoint, again, U star is the adjoint, U star times U is the identity matrix, we say that U is unitary. So just a quick reminder, given a matrix A, its adjoint A star is the conjugate transpose. Okay, so as it turns out, this is a little bit tedious, but sort of easy to check whether a matrix is unitary. Given a matrix U, just construct its adjoint, and then use matrix multiplication to write U star U. As an aside, unitary matrices are super, super important in lots of applications. Some of you may have heard of principal component analysis, for instance. Really important there. Really important in a matrix factorization called the singular value decomposition. So lots of places where unitary matrices come up. Okay, here's an example of a matrix that's unitary, and I won't go through the illustration here. Maybe have you just use Sage to do this, but when you calculate U star U, what you get is the identity matrix, so U is unitary. Here's another example of a unitary matrix. This is a matrix of zeros and ones, a matrix P. It's pretty quick to identify also that this matrix is unitary. P transpose times P is the identity, in fact, because the matrix is real. An aside here also, this matrix is called a permutation matrix. It turns out that there are 5 factorial permutations on this identity matrix, this 5 by 5 identity matrix, and together the set of all permutations of an n by n identity matrix forms a special mathematical construct called a group. So we're not talking about groups in this class, but you will talk about groups if you take an abstract algebra course, and that's an important consideration. Here's a cool theorem. If U is unitary and of size n, then U is non-singular, and the inverse is the adjoint. So this theorem is pretty quick, almost by definition. So by definition, U is unitary if and only if U star U is the identity. Of course, if there is a matrix such that that matrix times your matrix is equal to the identity, that other matrix is the inverse of your matrix. And that pretty much completes the proof. I'll go ahead and state this next theorem without proof. This theorem relates columns of a unitary matrix to a set of vectors. So a matrix A is unitary if and only if its columns form an orthonormal set. So I'll just have you read the proof of this. This is an important result, that columns of a unitary matrix are an orthonormal set. So again, a set that's orthogonal where every vector is a unit vector. Just an example here is a matrix we saw previously. This matrix U believe it or not, columns of that matrix form an orthonormal set because we saw that it's unitary. Okay, and one last theorem that relates unitary matrices to inner products and norms. This theorem says that the inner product of u times vector u with u times vector v is the same as the inner product of u with v, and that the norm of u times vector v is the same as the norm of v. I'll go ahead and state this without proof here as well, but the take-home message, as it turns out, is that multiplication by a unitary matrix does not change angle between vectors, and it also does not change length of vectors. Okay, folks, that's it for this section on matrix inverse and the non-singular matrices. We talked about, built up to a theorem, a matrix is non-singular if and only if it's invertible, and then we saw the definition of a unitary matrix and some consequences of unitary matrices. All right, folks, have a great day. Hope you've enjoyed this video. Let me know if you have some questions, and we'll talk to you soon. Bye-bye for now.